Hi, everyone. I'd like to introduce you to Lesson 13, Visualizing Regression Results using the Standard Error and Confidence Intervals. This is one of the really common ways of visualizing regression results, and it's a really compelling way to convince your reader and give them a little more information at the same time on how confident you are about your results. So this lesson relies on a new concept called standard error. And I'm going to walk through this document, which contains code that you can run too. And I'm just going to verbally explain what's going on here. So first, for this explainer, you're going to need these four packages. Tidyverse, Modern Dive, Infer, and the Broom package, which is a new package that you all also have that's for tidying up data. So kind of like with a broom, it's kind of cute. And it says you need TextReg, but you don't actually have to worry about that. So what we use to visualize regression results here is something called the standard error. So imagine you've got your beta coefficient or your alpha coefficient. You know that these estimates, these statistics might vary slightly when you take a random sample here or a different random sample, right? Because all random samples differ slightly. So wouldn't it be nice if we could create a little band around our estimates showing, well, we estimated that the beta coefficient was here, but it could be anywhere around here. It's somewhere around here. We're 95% confident it's around here. That's what we're going to learn to do. So how do we do it? We use the standard error. Standard error, as you can see here, is a measure of how much a statistic varies on average due to random sampling. So let's break this idea down into parts. We know already that statistics are single numbers that summarize a trait about a sample of data. Some statistics describe a single variable, like the mean, right? They just take one vector. Some describe the relationship between an explanatory variable and an outcome variable, like beta in regression models. What we really want to know is a single value that summarizes the population, all of the cases in the universe on our topic. And that single value would be called a parameter. The parameter is the population equivalent of a statistic. So the problem is we can't see the population. We only get samples, right? So instead, we're going to gather single values that summarize a sample of data to get close to the population, right? And the best way that we can take a sample is we can take a random sample. Random samples are the best kind we can get because each case has an equal chance of being selected. This means that they're pretty representative of the population. In fact, if you take many, many, many random samples, the statistics from each sample, if you line them up from lowest to highest, they tend to cluster around the same value in a beautiful normal distribution, in a bell curve. That value that they cluster around is the true population parameter. This is called the central limit theorem, and we learned it in week 5. Here's the key thing. That distribution of 1,000 statistics that you got from 1,000 samples, that is called a sampling distribution. It is literally a distribution of statistics from samples, a sampling distribution. To show you what I mean, I'm going to show you a quick example. For example, we could use the diamonds data set, which has 50,000 diamonds. It's in the Tidyverse package. We could calculate the mean price of all these 50,000 diamonds to get a population parameter, which in this case is the mean. And we could find that the average price among 50,000 diamonds is about $3,932. However, what if we didn't have access to the whole population? What if instead we just got to take samples from it? So we can use the rep sample n function down here to take repeated samples. We're going to take, and I'm afraid that this has a slight error here. We're going to take 1,000 repeated samples where each sample has just 100 diamonds. 1,000 repeated samples, each sample has 100 diamonds. So we take 1,000 different samples, and then grouping by the sample number, we then take the mean price of each. And we're going to save that as something called stat. And if we look at the first 6 sample means that we take, it looks like this. See, we see that the mean price from all of these random samples varies a little bit. Great, so we generated a sampling distribution of 1,000 statistics from 1,000 random samples of the population. So what's cool is, if you visualize this as a distribution, because it is just one vector, so we can make a histogram of it. We can show how often low values happen, medium values, and high values happen. We can visualize it and create this visual. This is a sampling distribution, and this black line is the population parameter. And you can see that the population parameter is pretty much in the center of the sampling distribution. Central limit theorem, very, very cool. How did we do this? Well, using these functions, we made a histogram, just like you learned in chapter 2. And then we also used a new function called geom vline. It's make a vertical line, vline, right? And to do it, you have to give it something called the x-intercept, the spot on the x-axis where the vertical line begins. And we say, make it start at the population mean, at this single value. And so we said, make it start here, right at about $3,930 some dollars, right? Okay. So pretty cool. But wouldn't it be nice to be able to describe this sampling distribution better? For instance, we can see that these tend to cluster around this area, but they tend to be off a little bit too. How much do statistics from samples tend to vary in this sampling distribution on average? That is, first of all, called the standard deviation. And second, that is the standard error. How much do statistics in a distribution vary on average? So we can find out several things about this using percentiles, actually, like using a bunch of different descriptive functions. We can get the mean, and we expect the mean of this distribution to be very, very, very close to the population mean. We can get the standard deviation to show how much it varies on average. And we can also get percentiles to see like what percentage of cases are bigger than a certain value. So for example, the 2.5th percentile is probably out here. That means that 97.5% of statistics are larger than it. And the 97.5th percentile is probably out here. That means that 97.5% of statistics are smaller than it. What is useful about that range is that would tell us the 95% confidence interval. It would tell us when we take a bunch of samples, generally the statistic is within this range. In fact, not just generally, 95% of the statistics that we get are within this range. That is a 95% confidence interval. So how would we do it? Well, we can use our sampling distribution. Remember how we made a sampling distribution before? We saved it in an object called sampdist. I'm going to show you up here. Proof. See, we made it. We put it in this object called sampdist for sampling distribution. We can now create some summary statistics about that sampling distribution. We can summarize it by getting the mean statistic, by getting the standard deviation of the statistic, which in this case was the mean price, right? We can also get the 2.5th percentile of the statistic and the 97.5th percentile. Now, you should take a look at this. This is a new function right here. It's very, very useful, but it's new. It's called quantile, and it works very similarly to mean and standard deviation and min and sum and max, right? Very similar. You say quantile as the function, get me the percentile, notice the tile on the end there, of this vector called stat, and get me the value, which if you line them up, it would be the 2.5th percentile in position, right? And so we specify it there where we've made it a decimal, and we say, hey, if there are any NAs, please take them out. Don't worry about it. And we do the same thing for the 97.5th percentile. If we view this, boom, from the sampling distribution above, we can see that on average, traits vary around the mean by this much, and 95% of statistics are between this number and this number. Kind of useful, right? So here is the nifty thing. We can visualize this. Remember when I shared geom vline a couple minutes ago? Before we ran this function, where we made a histogram of the sampling distribution, and we made a vertical line that specified the population mean. We can add to that by adding a whole bunch of more vertical lines. For example, we can plot the actual mean of the sampling distribution, which should be very close to the population mean. We can we can show on average the range in which the statistic varies. So that's going to be the mean plus the standard deviation and the mean minus the standard deviation. Hint, that's the standard error. And then we can also plot the 95% confidence interval, which is not on average, but in what range do 95% of the statistics you get due to sampling error lie? And you'd plot them by, just like we did before, using a data frame, calling a specific vector that has just one value in it. So we're just saying like x-intercept equals 3,218 for this one and 4,000 and whatever for that one. Let's take a look. Boom. There you go. We can see there's a black line here, and that's the population mean. We can also see right next to it is a red line. That's the sampling distribution mean. It's supposed to be very close to the population mean. This dashed line is the standard error. It shows on average how much do statistics vary in this distribution. And then out here is the 95% confidence interval. Although on average, the mean price tends to vary around here, we are 95% confident that the mean price is somewhere in this zone. And that's useful, right? Because the mean price could be 0. The mean price could be 1,000,000. But we are 95% confident that it's somewhere between this specific zone. That's helpful. Here's the thing. When we look at this, you might be noticing something. There's a shortcut to finding the 95% confidence interval. Do you notice how the standard, one standard deviation out from the mean is right here? So this is the mean. This is one standard deviation away. And actually, this is about 2 standard deviations out from the mean. The confidence interval tends to be 2 standard deviations out from the mean. Fun fact, this is true for all normal distributions. The 2.5th percentile and the 97.5th percentile on all normal distributions tend to be 1.96 standard deviations away from the mean. Just about 2 standard deviations out from the mean. It's a neat trick. Now, not all sampling distributions are normal, but they generally tend to be. They generally tend to be within that zone. So it's a very useful trick for finding the confidence interval. Let's test it out. So before, we ran this function, which gave us the mean, standard deviation, and the 2.5th and 97.5th percentiles for our sampling distribution. We can also calculate them using the standard error shortcut. Remember, the standard error is the standard deviation here. It's how much the statistic varies in a sampling distribution. And we can see that we're calculating it 2 ways. One of them is to take the mean minus the standard deviation times 1.96, and that's going to take you about 2 standard deviations to the left of the mean. One of them takes you about 2 standard deviations to the right of the mean. And if we glimpse our new data frame, which has a bunch of columns, so we're going to glimpse it, we can see that, yeah, our standard error shortcut gave us very similar estimates for the 95% confidence interval. They're very, very similar. They're just a little off, but they're very similar. We know that the ones we calculated with the percentile function are correct. They are the real ones, but the standard error shortcut is very effective too. So here's the problem. Usually we don't get to see sampling distributions, and we definitely don't get to randomly sample from the population many times. After all, that's expensive, right? You can't survey all Americans many times. It's hard enough to survey them once, right? However, we can still figure out the confidence interval, and we can do it using one of 2 methods: a computational approach or a theoretical approach. This may sound familiar. This is analogous but different from how we get p-values. So let's imagine that we take just one sample using the sample n function, where we grab just 100 diamonds from the original 50,000 diamonds dataset. And also, we're just going to get rid of all the other information. We don't need it anymore. In the computational approach, we can bootstrap our way to a sampling distribution, even though we don't have access to it. Even though we can't see the actual one, we can work really, really hard to get close to it. How do we do that? Well, instead of sampling from the population a bunch of times, we're going to sample from our own sample. It's really cool. It's called resampling. Resampling is where, let's say, for a single sample, let's say you want to take 100 diamonds as you have 100 diamonds as one sample, and you want to make a new resampled 100 diamonds. What you do is 100 times you'd go into the bag of diamonds, you'd grab one, you'd write down like its ID number or something, and then you'd put it back in to the bag, and you'd randomly draw again. What this means is a resample, as opposed to a sample, can have the same diamond show up multiple times. It can have the same case show up multiple times. This means that resamples are affected by random sampling error. It's not super important that you guys can reproduce this part perfectly, but it's more about understanding how it works. So bootstrapping says, hey, I can't make a complete sampling distribution because I can only take one sample, but I can simulate what random sampling error would look like by taking a whole bunch of different samples from my own sample. And if I do that, you'll end up with 1,000 resamples. And you can take the statistic from each, and they'll plot an approximate sampling distribution. What do I mean? Well, for example, we can calculate the observed statistic from our sample of 100 diamonds. So that's going to be the mean price from 100 diamonds. We can also use the generate function from the infer package, changing it to something called bootstrap. Remember how before we used to use permute, now we're using bootstrap. And after taking 1,000 resamples, we're going to calculate the mean price for each. Then we're going to take the percentiles from what is a very, very long list of 1,000 different mean prices from all the resamples. And you can see that our confidence interval is, well, it's not great, but it's pretty close, you could say, right? It's kind of helpful. In contrast, we can also use a theoretical approach, and this is the one that you guys are going to be using. So the theoretical approach says, hey, thanks to the hard efforts of mathematicians, people have figured out how to calculate the standard error for a whole bunch of different statistics. Each formula is slightly different, which is why I'm going to teach you none of them. It's a bit of a choice, and if you look them up, yeah, you can probably figure them out. And if you have questions, feel free to ask. But we're going to go straight to how do you use it. So the standard error can be calculated from a sample, and all of the formulas, even though they're slightly different each, all of them have two big components that affect your standard error. One, how much variance is there in your variables? And two, what is your sample size? This draws on the law of large numbers. Remember how we did the Skittles experiment? And when we took bigger samples, not more samples, but bigger samples, the sampling distribution actually got narrower. This has to do with that. This gives you a narrower standard error if your sample size is larger, and it gives you a wider standard error if your sample size is smaller. This means that it basically means that your 95% confidence interval is going to be wider because you're less sure of the true value of the population parameter because you simply looked at fewer cases. So this is a really nice shortcut. How do we get the standard error? We can find it very easily in our regression tables. Let's take a peek. So for example, we can, on our sample of 100 diamonds that we made before, we can run a regression model where we predict the price of the regression, the price of the diamond based on the carat, how big it is, and the depth, which I assume is kind of like how shiny it is. If we use the summary function, we can see, yeah, right next to the estimate, which is where our alpha and beta coefficients are, right next door is the standard error. Holy crap, it's been there all along. And this shows in the same units that this is what the beta or the alpha or the beta coefficient tends to be around on average. Here's the nifty thing. Using that broom package, we can use this function called tidy that's going to extract that model table. And it's going to put it in a nice data frame right here. See how up above this coefficient table is exactly the same thing as what's in this table. It's just manipulable. It's in a data frame now. So now that we've got the standard error, we can actually calculate the lower confidence interval for each variable and the upper confidence interval quite easily. We would do it like this. See, we're going to take our model object, we're going to tidy it, and then we're going to mutate each row, creating a new variable called lower CI, that is the beta coefficient minus the standard error times 1.96, standard error shortcut. Alternatively, we can use the upper confidence interval. We can make that by taking the beta, adding the standard error, and multiplying it by 1.96. And when it comes out, boom, there it is. We get a nice confidence interval.